thank you for coming. And what I want to do is start off with a little bit of an overview slide. Basically what I want to do is talk very quickly reviewing the basics of GPC calibration and show how there are some common techniques to improve the molecular weight range that this calibration curve can be applied to, and how technology from Tosoh Bioscience is improved upon what's been used conventionally. And then get into some more details regarding columns made with this type of technology, and then show how the capabilities of this technology comes to a full fulfillment when they're run on the EcoSec GPC system. And then I'm going to conclude with an update on some work I've been doing with Excel and coming up with methods to use spreadsheets to model and do different kinds of thought experiments with how different kinds of columns can be used in combination. So this is a typical GPC calibration curve, and what we have on the x-axis is the retention volume. For the separation, on the y-axis, we've got the molecular weight. And for very, very large molecules, they're going to be the first type of material to elute from the column. So they're eluting in the excluded volume. Very, very small molecules are coming out at the end of the chromatography in the included volume. And then in between, we have a calibration curve where the selective permeation takes place. And what happens here is the polymer elutes as a function of its molecular weight. And when the chromatography is seen, which you see down here, large materials coming out first in the excluded volume, followed by smaller material that's in the selected permeation range, and then the included volume. And if you look at calibration curves in catalogs from Tosoh or any other company that makes GPC columns, typically they'll have 8 or 10 or 12 different types of columns and their calibration curves laid on top of each other. And kind of a pattern that you can see when you look at that is there tends to be a trade-off between the resolution that a particular column can provide and the linear range across which that resolution can be used. And so that's what I'm trying to show here with these couple of curves. Basically, if you have a column with a very wide molecular weight range separation capability, typically we have less resolution in terms of the shape of the slope, compared to other columns where this type of material in the column is giving a very shallow slope, which means great resolution, but then typically there's a trade-off in that the molecular weight dynamic range is smaller. So what you can do if you want to increase the resolution, of course, there's a couple things that are done. Typically you could add more columns of the same type. So take two columns that have identical material in them, hook them together, you're increasing the amount of pore volume in the column, and you increase the resolution. Or the other thing one can do, of course, is to use a smaller particle size in the column. And then this is kind of the main part of what I want to talk about today, which is how to increase the linear range across which you can do the chromatography. So there's basically two approaches that have been used. One is to use a series of columns where each individual column has a different pore size. So you would have a series of columns with different exclusion limits, if you will. That's one approach. Another approach has been to take the material that would be in those individual columns and mix them together, creating a mixed bed column, and then connect a series of those types of materials to each other for a mixed bed. And the idea is that you would take these individual calibration curves, and by either hooking them together in series or mixing the beads together and then packing the column, you would create a calibration curve that had a wider linear range. And then this is a schematic kind of showing what this looks like. The idea here is, in this conventional approach, you might have different types of particles. So you might have particles that have large pores, medium pores, and another type of particle that has small pores. So the idea is you can pack one column with large pores, a second column with medium pores, and the final column with small pores, attach them to one another, and you'll get a wider linear range. Or you can take these materials, these individual types of materials with the different pore sizes, mix them together, and then pack a series of columns, creating a mixed bed type. So this has been the traditional approach, and there's a problem though with that. If the individual columns that you're attaching to each other, or the beads that you're mixing together into a mixed bed column, aren't on the same slope in terms of their linear calibration ranges, you can end up getting artifacts in the chromatography that will look like peaks, but really are just the fact that these linear ranges are not overlaying smoothly enough to give you decent data. So because of that problem, Tosoh developed a multi-pore type of packing. So the idea here is, instead of having individual particles that are either large pore, medium pore, or small pore, what we do is we take the particles and we have a distribution of pore sizes within each particle. And then you would pack a series of columns with that type of material. And what that does is that smooths out any errors or incompatibility between the different individual shapes of these individual calibration curves. And here's an example where in the top chromatogram we have phenol resin separation where we're using the sequential column approach. We have a G4000, 3000, 2500, and 2000 XL. And you can see there's a little bit of distortion in the chromatogram. And basically that's due to the fact that for these sets of columns that were used, the linear calibration curves weren't ideally optimized with each other. However, if this is run on a multi-pore type of column, then you get the smooth curve, which is more accurately representing the distribution of the polymer within the sample. So we have this multipore technology in conventional large columns and larger beads, 10 micron type beads. But also we have what are called super multipore columns, super multipore HC columns, and these are designed to have ultra low polymer absorption. They still have this multipore technology to improve the linearity without getting the chromatogram distortion. And they're also packed into semi-micro columns. So what this means is we're using a smaller column. It's a shorter column and smaller diameter. And what that gives you is run times that are 50% faster. They're twice as fast, basically, because the column is half as long. And then the solvent consumption is 85% less because the column is half as long, and then we're running it at a third the flow rate. So that's saving us 85% on the solvent costs. And what this graph is showing here is calibration curves for polystyrene, where we're comparing this more conventional approach with the series of columns where each type of column has a particular pore size range in it. That's what we're showing in the purple, to conventional mixed bed type, which is in green. And then the blue here is the super multipore HC. So this is the material where the particles have a distribution of pores within each particle, and you can see that that's giving the best resolution and linearity of the three methods. And what we have now showing now is electron micrographs of the individual particles from the three different types of super multipore columns that we offer. And what you can see here is that the columns are available in 3 micron, 4 micron, and 6 micron particles, which are small particles for GPC use, but because the column is half the length and we're running at a third the flow rate, it works fine for polymers. There's no issues with shearing or anything like that. And also you can see that the beads are very uniform, so it's a monodispersed type of technology as well. And if you do pore size measurements of the particles, and you compare the distribution of pore sizes that are in the super multipore type of column with a conventional type of column, you can see how in a conventional column, basically the pore size distribution is fairly narrow, where it's very, very broad on the super multipore column. So that's where we're getting that excellent linearity and wider range. This is 3 calibration curves showing the 3 different materials that we have. So the material here, the HCN material, is the 3 micron, and then we have the 4 micron in the M, and the 6 micron is the H. So we're getting a very wide useful range, and if you're looking for the oligomer region or smaller polymers, then the N material is giving very good resolution. So kind of a summary here of these super multipore HC columns is these packing materials have a broad pore size distribution, and what that gives is the ability to not have any inflection point in the calibration or distortions in the calibration curve or the chromatogram due to an imbalance between the different types of pore sizes being overlaid. So you're getting a really very linear calibration curve, so there's less error and a more accurate molecular weight measurement. The large porosity range gives you high resolution is in the oligomeric region. And also because of the concept here, there's less lot-to-lot variation because we're not having to try to match different batches of beads to keep the calibration curves overlaying in a linear fashion. And also small particle size, which is providing for high speed and high resolution with low solvent consumption. And this is just a chart showing how a conventional column would compare to a semi-micro column. And basically, conventional column is going to be 7.5 or 7.8 millimeters in diameter. Semi-micro column is smaller. We're also half the length. And so the benefits, once again, are saving on the runtime as well as the sample consumption, or the solvent consumption. And then this chart shows for these individual types of super multipore columns the separation range. So the HZN is good up to 50,000, HCM up to 1 million, and then the Super 8Z up to 10 million. So there's quite a range of products you can choose from there. So when you're using these smaller columns, what you need to really think about is how the volume of the system that you're running these columns on might affect the separation. And what we're talking about here essentially is the band spreading that happens within an HPLC system due to aspects that are not related to the column. Things like eddy diffusion and longitudinal diffusion, and there's things that within the column that happen as well. So the idea is that if you run a small column on an instrument with a very large dead volume, you're going to lose resolution just by, in essence, Brownian motion and the randomness that happens as molecules move through a column. And to show that, what we have here is a chromatogram using a Super H column. Actually, we're using 4 of them, using THF as the mobile phase at 0.35 mils per minute. And we are running the same column as samples and mobile phase, same flow rate, on 2 different systems. So one system is our EcoSec GPC system, which is designed to have very, very low dead volumes, compared to a conventional GPC system. So in purple, or red here, this is the resolution from the EcoSec instrument, and essentially we're getting many more peaks with baseline resolution, and we're able to see many more peaks compared to running that same column and samples on a conventional system, and the reason for that is the lower dead volume of the system. And so here's a picture of the instrument, and part of the reason that we get this low dead volume is the design of the system is where all of the components are essentially in one box, if you will. And so that lets us place the individual components very, very close to each other so we can use very, very short lengths of tubing. We also use a very low volume in our flow cells, and the combination of all that is when you run very small columns on this instrument, you're able to maintain good resolution. And here's some chromatography simply showing how a chromatogram with in a conventional column versus the Super Multipore, or sorry, the Super HZ column. When run on the EcoSec, we're able to maintain excellent resolution, but once again, this is on a smaller column, so very fast run times. And if you're using expensive solvents, something like HFIP, the ability to run at 1/3 of the flow rate and still have really good resolution, can be a significant cost savings. So we have a customer who that was his main attraction to the instrument. He was using HFIP, of course it's very expensive, and the fact that he could reduce his solvent usage by 85% by simply choosing an EcoSec GPC system made all the difference to him. Another feature of the instrument is the dual flow refractive index detector, and what that provides is superior performance in terms of baseline stability. So what we're showing here are chromatograms where we're running the same column samples, mobile phase, etc., but on 2 different systems. We're overlaying 5 chromatograms on the EcoSec GPC system, and you can see that there's virtually complete overlap. There's really no drifting or no difference between any of these individual injections. However, when that same sample is run on a conventional refractive index detector, you can see how the peaks are offset from one another, and that's going to lend to inaccurate data. And the way this dual flow system works is, in a conventional refractive index detector, the material that's in the reference cell of the detector is not flowing. It's a stagnant pool of THF typically, and as you know, THF will degrade over time. So if you're running samples over a weekend or overnight, if the material in your reference cell is degrading over time, but you're having fresh solvent flowing from the column for your samples, there's going to be a continual change in the difference in refractive index between those two materials, which you will see as drift in your chromatography. With the dual flow design of the EcoSec GPC system, we are continuously flowing solvent through the reference side of the cell as well as the solvent side. So we're always able to account for any degradation that's taking place in the mobile phase. Another feature, of course, is when you're working with GPC, the precision of the pump flow is very, very important, even more important in GPC compared to HPLC. And that's because what we're really after, of course, is the molecular weight of the polymer, and that's the log of the molecular weight that's related to the elution volume. So it's very, very critical to have extremely precise flow rates. And one of the aspects of a lab that can affect the precision of an HPLC system is the room temperature. And then what happens here is if the room temperature is changing, the temperature of the solvent will change over time, which changes its compressibility, which then in effect changes its flow rate. So to illustrate this, we've got chromatogram overlaid here with an intentional change that we've made in the room temperature. So if we change the room temperature, we cycle it from 19.9 up to 19.95 and back down and up and down again. And then we plot the elution time for a given peak. On a conventional system, you can see how the change in the temperature of the room is affecting the elution time of the molecules. They're completely in sync with one another. However, if you do this same experiment with the EcoSec GPC system, of course, the temperature in the lab is changing because we're intentionally doing this, but the retention time and elution volume for the sample remains constant. And that's because the instrument has an oven system that keeps the pumps at a constant temperature. And so if you have any swings of temperature in your lab, they're not going to have any effect on the precision of your GPC analysis. And here's some some charts showing reproducibility data, and this is done on polystyrene standards. And basically what we're seeing with these temperature control pumps is we're getting excellent retention time precision. So CVs for retention time are on the order of less than 0.04% a day. And then when you translate that into the molecular weight precision, molecular weight CVs can be less than 0.2% or less on a day. Also, the instrument and the software is all designed around being optimized for GPC type analysis. So it has all the calculations needed for MW, MZ, and MN type calculations. And then also a very nice interface where any changes in valve positions or injections or auto sampler are reflected in the screen that's available. And a very nice feature also is that the column oven is unique in that it can hold up to 8 30-centimeter long columns. So if you are in a lab where you're using lots of different columns, you can keep them all at the same temperature very conveniently with this column oven. And then this is a chromatogram showing a whole series of different polymers. We've got epoxy resin, polycarbonate, polyvinyl chloride, polystyrene, etc., run on the the TSK gel Super Multipore HZ, showing very nice separations. And we're running 4 columns here, and we're getting this analysis done in 26 minutes or so. Okay, so are there any questions on the Super Multipore columns or the GPC system? Okay, so the next thing I'm going to do is shift gears completely, and I'm going to talk about something I've been working on a little bit, and this is this Excel-based column selection tool. And the motivation for this was twofold. One of them is I would get frequent requests to make a recommendation to a customer about which Tosoh columns to use versus the type that they were using currently from another vendor. And simply looking at charts from different vendors and columns with different dimensions and different particle sizes, it was challenging in my head to try to keep together and figure out what's the best thing to recommend. So that was something I was running into. And what happened is I came across a separation report that Tosoh Bioscience has on our website, and this is Separation Report 28. And what this shows is something that I found very interesting, and it's basically, the idea is if you run a series of molecular weight standards on an individual column with a given pore size and a second column with a different pore size, and you just add up the numbers that you got when you ran them separately, you just do a calculation, you just do math, you can get a calibration curve that matches almost exactly what's observed when you do the experiment. So the idea here is basically the separations with GPC, it's very, I don't know, mathematical is the right word, but essentially you can look at a calibration curve, and if you can come up with a scheme to mathematically add those calibration curves to each other, that's going a long way towards predicting how it's going to behave when you actually run the sample. So the combination of me coming across this chart and having a need to look at how different calibration curves, comparing different types of columns to each other, that's what the motivation was. So as the chart, this shows here the status. This is a work in progress. Of course, I had great ideas how far this was going to go, and I'm partway along the path. But I just want to share with you where I've gotten so far and just show you a little bit about how I've been doing this. So the first step is we want to take the calibration curve, and we want to take it from being something printed on a piece of paper into numbers that we can use with Excel. So we'd scan this into our computer, and this is where I spent a lot of time, was finding a software package that would let me easily convert this 2D plot into XY coordinates. So I came across this software package called Graph Digitizer. It works very, very well. It handles the fact that the y-axis is logarithmic, and that you can do multiple curves with one setup. So that's worked very, very nicely. And so what I'm able to do now is I can take any set of calibration curves that I get off the internet or from a brochure or something, scan it into the system, and then I can convert it into an Excel type of format. And then I can simply do math by adding whatever curves I'm interested in comparing, and I will get a result, which theoretically should be how those columns would behave if you actually ran them. So in this example, I thought, let's do something really, really crazy. Let's take the column that we offer with the smallest pore and the column with the largest pore and hook them together theoretically in the model and see what happens. And so this is something that you would probably never do in reality, because typically you would want to have different materials that have a more continuous relationship to each other. But essentially what we do is we take the G1000 calibration curve. So basically this is small pores, so it's showing a good separation up to 10,000 or so, but then everything larger than that's coming out in the excluded volume. And then we've got the G7000, which of course is able to give good resolution across a broad range of materials. I'm sorry, that's what this one is. Simply add them together, and this is the composite that you would get. And then the other thing I thought about, well, what if we took the same column, and what the heck, what if we hooked 10 of these together? It's something you would never do, once again, in a real lab, but I wanted to see how that would affect the resolution. And indeed, the more columns we're hooking together, the larger pore volume we're seeing, and the more shallow the slope is, so the better the resolution that we're obtaining. So this is kind of pretty much where I am now. I've got the tools in place where I can play with these things and make the spreadsheets make sense. And so now the next step for me is to figure out how to compare columns that maybe have different geometries or different particle sizes, or even using different molecular weight standards for the calibration, to begin to expand how this tool can be used. So that's what I've been doing with the Excel technique. And oh, here's what I did. Here's where I did it with, with 10 of the same columns. So if you have one G7000 column, you get not much resolution compared to if you were to hook 10 of them together, but it's probably not something you would do in reality. Another thing, of course, I can do is this. I can compare how mixed bed resins are comparing with super multipore type resins and how that's comparing with using a series of different columns. Okay, so my conclusion is TSK gel super multipore HZ columns provide accurate wide linear range separations. They're designed around the semi-micro concept, so these smaller columns provide a time savings and money savings because of the low flow rate and the quick runs. And the EcoSec GPC system, when combined with these semi-micro columns, offers superior performance and versatility because you're able to really get a lot of resolution out of small columns when they're run on a system that has very, very low dead volume. So, thank you for coming.